Hello friends, I Professor Darshan Thakur from Terna Engineering College Dharamshi welcomes you on my YouTube channel for this subject head Digital Communication. Friends, our today's objective behind this session is to learn this single carrier digital modulation scheme whose name is nothing but frequency shift keying, or more prominently we can call it as a binary phase shift keying. So most of the time that can be called it as a BFSK. So basically this BFSK falls under the category of single carrier continuous wave digital modulation, right? Now the question arises ki why it is being called it as a single carrier continuous wave digital modulation. So the answer is nothing but what we can transmit either 1 or 0, means only one bit is being transmitted during each and every signaling interval. That's why it is being called it as a single carrier. Now as far as this continuous wave digital modulation scheme, this terminology is concerned, so see, in case of modulation, as I told you earlier, there will be an involvement of two different test signal, carrier signal and the modulating signal. So obviously the nature of modulating signal is in discrete form in case of this digital modulation scheme, but the nature of carrier signal is in analog form. So that's why it is being called it as a continuous wave. So let us quickly go through the whole modulation and demodulation process involves in case of this binary phase shift keying, right? So friends, we need to remember that as far as these digital modulation schemes are concerned, so there are three different approaches we can have as far as this entire modulation or demodulation process is concerned. So these three important approaches are concerned as far as single carrier or multi-carrier modulation schemes are concerned. So the first important approach is nothing but how we are representing these two probable symbols. Which two probable symbol? Binary 1 and binary 0, because our information bearing signals are in form of ones and 0. The nature of that information bearing signal is in digital form, right? So the representation of this signal is the first approach. Obviously second approach is nothing but how to generate the desired envelope belongs to either it is phase shift keying, frequency shift keying, amplitude shift keying, or the quadrature phase shift keying, whatever it may be. This is the second approach, and the last important approach is nothing but what? The detection. How we can extract the information bearing signal which was given to or which was transmitted by that modulator towards the demodulator, or which was transmitted by transmitter towards the receiver. So let us quickly go through the first approach, in which what exactly we are doing. First of all, we need to define how this binary frequency shift keying technique works. So as its name indicates here, our area of interest is to transmit some sort of data, right, by modulating the frequency of this unmodulated carrier signal with respect to the amplitude of this digital modulating symbol sequence. So this is the basic logic behind this binary phase shift keying. So for that purpose, first of all, we need to understand the basic block diagram of this binary phase shift keying modulator or binary phase shift keying generator, right? So before going for this generation process, as I told you earlier, first of all we need to understand the interpretation of binary 1 and 0, means how these two symbols are being represented. So as you can see, this is the generalized form in which that sinusoidal signals are to be interpreted with this cosine term, right? So in case of this binary phase shift keying or in case of this binary frequency shift keying, the carrier frequency is being splitted into two different signal frequencies to represent binary 1 and binary 0, right? So for sake of our understanding, for binary 1, that can be called it as a SH of t, means the highest frequency or the high frequency is being allocated to binary 1, and SL of t means what? The low frequency is being allocated to binary 0. Now how binary 1 is being represented here? See, mathematically how it is being represented: square root of 2p into cos of 2 pi f naught plus omega, right? Where what the square root of 2p, that is nothing but what? The desired amplitude of that carrier signal represented by binary 1. So here this binary 1 is being tuned to this highest frequency, that can be called it as omega with respect to this t. At the same time, how this 0 is being represented? 0 is being represented in a same way as compared to binary 1, but the only difference is what? As I told you earlier, the lowest frequency is being allocated to binary 0, so which is denoted by this term called it as a minus omega, right? So for sake of our convenience, if suppose this can be called it as equation number 1, and this is nothing but what, equation number 2, right? When these two equations are being combined, so the overall representation of this carrier signal, that can be rewritten in this way: s of t equals to root 2 times of p into cos of 2 pi f naught plus b of t into omega t, where obviously as far as this b of t is concerned, this b of t represent what, the unipolar binary symbol sequence which is being given to this BFSK modulator or BFSK transmitter, which consists of binary 1 or binary 0. If it is binary 1, then highest frequency is being allocated omega. If it is binary 0, so this whole term will become minus of omega, right? Lowest frequency is being allocated. So in this way, this is the first important approach, that is nothing but what, how to represent binary 1 and binary 0. Now the second important approach is nothing but what, how this envelope is being generated. Okay, so this is how the binary frequency shift keying modulator or generator will look like, right? As we are very much aware of this thing, this high and low frequency is being assigned to binary 1 and binary 0 for the purpose of transmission, because from application point of view, most of the time this binary phase shift keying technique is being used in case of this high frequency radio transmission ranges from 3 to 3 megahertz. Or again, another important application of this binary phase shift keying technique is nothing but what, most of the time it is being used in case of your coaxial cable based local area network for high frequencies. So for the transmission of radio frequency ranges from 3 to 30 megahertz, this binary phase shift keying technique is being used, right? So ultimately the overall story of this binary phase shift keying is nothing but what, the carrier frequency is being splitted into two different signal frequencies to represent binary 1 and binary 0. So accordingly, this is the input binary sequence which is being given to the input of this BFSK modulator. Once that input is being given, it is being equally applicable to two different channel, upper and lower channel, right? The upper channel consists of level shifter along with this signal multiplier. Similarly, the lower channel consists of level shifter and this signal multiplier. Another additive block which is being mentioned within this lower arm is nothing but what, inverter, right? Because these two signals are complements to each other. Which two signals? PH of t and PL of t. To have the PL of t from this given binary sequence, it is being passed through this phase shifter, or we can call it as an inverter, right? So that's why PH of t and PL of t, these two are the complements of each other when these two signals are being given to this level shifter, right? So what kind of task is being allocated to this level shifter? Level shifter basically it will accept either binary 1 or binary 0, right? So for this binary 1, plus certain positive voltage is being assigned to this binary 0. Obviously the lower or the negative voltage is being assigned, so it will convert this plus 1 volt into the desired amplitude along with this highest frequency, that can be treated as a root p TB into PH of t, right? Where root p is nothing but amplitude of binary 1, right? And this PH of t, it is nothing but what, the way in which we can transmit that signal with the help of high frequency, right? And after that these signals are being given to the signal multiplier, right? So as far as the signal multiplier is concerned, which is being mentioned with these two, we can say that the carrier frequencies, right, represented by square root of 2 by TB into cos of 2 pi FHT and square root of 2 by TB into cos of 2 pi FL of t, right? Means the high and low frequency is being multiplied bit by bit corresponding to either binary 1 or binary 0, and finally these two signals are being added with each other to generate the desired envelope of binary phase shift keying signal, right? Now another interesting story about these two carrier signals are nothing but what, these two carrier signals are orthogonal to each other, right? And during the same signaling interval, it will produce the output due to either upper modulator or output due to the lower modulator. Means mathematically it is not possible to generate the output due to the upper as well as lower modulator, because as these two signals are complement of each other. So during signaling, each and every signaling interval, the output is produced due to the upper or lower modulator.